eukaryotic cells is called 45S. 45S is a sedimentation value, not a molecular weight. That refers to how quickly it sediments in an ultracentrifuge measure. That's different than molecular weight because it's dependent on molecular weight as well as shape. A feather would go through liquid prel quicker than or much slower than a pearl would, even if the pearl weighed the same amount as the feather. So that takes into account both of those. That precursor RNA contains 3 of the eukaryotic ribosomal RNAs in there, 28S, 18S, and 5.8S. The 4th ribosomal RNA is the 5S RNA, there it is down there. It's encoded in another set of repeated genes on another set of chromosomes. These guys are synthesized like this as one big precursor. For stoichiometric reasons, you make 1 to 1 to 1, 18 to 28 to 5.8. So that each ribosome has a copy. You don't make any wasted RNA that way. Single regulator. The RNAs are modified, or some of the bases in those RNAs are modified. They can be adenylated, they can be methylated. You can see some of them that are there. And those modified bases have signposts or signals to which the small RNAs that process these things attach. The RNAs are called snow RNAs because they're like the snRNAs, but the snow refers to the nucleolus. So these small RNAs are specific to the nucleolus in particular. That SNR, that U3 RNA is part of the SNO3 RNA processing enzyme. These processing complexes that also have that uRNA recognize the nucleotides, and they're led partially there because of these modifications. You can see here that some of them can be pseudouridine and they're modified. Here's one that's methylated, right? Methylated at the ribosomes, 2O-methylation, modification of adenosine residues in this area. So a lot of the adenosines along here are 2O-methylated. The ribosome group is methylated. Ribose group is methylated, which is a recognition site for these guys here so they can help you line up and process it. We said that these things are made in the nucleolus. If you look at the nucleolus, it's separate from the nucleus of the cell. There is no membrane that outlines it there. This nucleus has different structures in there. You can see within the nucleus is a fibrous sort of a structure. We think that ribosomal processing, ribosomal RNA, takes place in these regions here. All these dots, they're called the granular component. That's where the processing occurs. Synthesis occurs between this horseshoe-shaped thing, which is called the dense fibrillar component, and something inside that's called the fibrillar center. Sort of around, right between, very close to the ring there. We think that's exactly where the ribosomal RNA synthesis occurs, and then the precursor moves down into these smaller granular components where it's processed. Okay. So today I want to talk a little bit about tRNA, transfer RNA. You've all seen this picture, this picture. This is a picture that was developed, or a structure that was developed by hand. So this is before we sequenced RNA, before anybody had a structural picture, crystallographic picture. And the people that, the guys, there were 2 guys actually that did this. What they did is they took this RNA and they just shifted it around, moved it around, played with it with a pencil and paper to identify the position where they could maximize the number of intramolecular hydrogen bonds. And when they maximize that number, forming the greatest number of hairpin loops and so forth, the structure they got with this 4-leaf cobra. And it turns out that they were absolutely right, that the number of bonds are maximized, and that there are 4 main domains of this tRNA molecule. One up here, which is called the acceptor stem. This adenosine residue up here, which is present on all tRNA molecules, is where the amino acid is attached. This is the amino acylation site. Down at the opposite end is the anticodon, and this is the triplet code, which is part of the genetic code. We'll talk about that in a minute. The 2 other arms are called the the 2 other regions here are called the D loop, because there's a D pseudo-U residue in here. The other is called the T pseudo-U loop because it has a thymidine and a pseudouridine in there, so this is the T pseudo-U loop. And the only other thing is the so-called variable loop. This variable loop is like an umbilical cord. The tRNAs vary from about 80 or 90 nucleotides up to about 125. look at all of them, they have exactly the same structure. The difference in the length of those occurs in this variable loop. It sort of gets bigger or smaller. The rest of them, if you took all of the tRNAs in the cell and you put them on the screen and line them up, they would come right out at you exactly in that position, and that's extremely important for their function. We'll talk about that. Since we've done this, since these guys did this loop structure, the crystal structure's been done. Here's the crystal structure in two different ways. If you take this T loop here and you fold it over so it sits on top of that D loop, right? And then take the stem loop and bend it down like this, you get this structure. You can see here's the yellow loop, right? The T loop, it's folded over the D loop there, the T pseudo U loop folded over that D loop. That's this guy folded over. And this guy bent down here so that you get this L-shaped structure. And this is the exact structure of the tRNA molecule, of all the tRNA molecules. This is just one where they rotated it 45 degrees or whatever into the board, so you can see that acceptor stem is going back into the board, and here's the loop coming out at you. So even after they did the crystal structure, it turns out they were right, and it turns out that all the vectors are represented in these loops, so that intramolecular bonding is there. And it sort of tells us something, that RNA molecules will seek out the secondary structure that maximizes their intramolecular hydrogen bonds. So it's sort of like, almost like protein folding in that respect, maximizing those bonds. Okay, so the genetic code was, the genetic code that we know it, or the one that we talk about all the time, was elucidated by Ehrenberg and Lieder, and they got the Nobel Prize for doing so. And essentially what they did is they were able to identify which of the triplet codes coded for which amino acid. And they did the experiment like this. Essentially what they did is they isolated tRNAs, and then they had radio labels once again. The timing is so important. The radioisotype codes were available, and they were able to radio label some of the amino acids. So they took a mixture of tRNAs and they threw in a lot of all the amino acids, which were unlabeled except for one. They labeled one. For instance, this was phenylalanine. Then what they did is they took ribosomes and they essentially washed these ribosomes. They isolated them and washed them out so they didn't have the messenger of the tRNA there. And then they inserted in their triplet code that they could insert in there. So they put that triplet UUU inside this ribosome. And if they took this mixture here, where the radioactive, so which one's radioactive? Whatever, I'm not sure. But if they took this and they had the radioactive phenylalanine there, and you took this tRNA mixture and put it into a ribosome, and the phenylalanine, right, if this was a UUU, the phenylalanine, the tRNA that had the AAA anticodon, would complex with this guy here like this, right? And then you could wash them through a filter. So after you took the ribosome, let the tRNA bind to that UUU site, you put it over a piece of filter that allows the tRNAs to go through, but not the one that was there. Okay, so this is the one where here's phenylalanine. Oh, that's proline. So that's what they've done is they've taken, in this case, they have a label proline, the pink guy, right? They put it in, they put all the tRNAs there, they let them interact with that ribosome with phenylalanine, the AAA, right? Forms a complex with the pseudo messenger RNA, the triplet they put in there, and then you wash through all the tRNAs. This guy's labeled, he doesn't match, he comes on through the filter, the radioactivity goes through, and you say, okay, so this time we used proline that was radioactive, it didn't bind to the ribosome, it went through the filter, so UUU does not code, it's not the anticodon for proline. You repeat the experiment, right? Using different radioactive labels, and in this one you happen to use phenylalanine, which had that AAA anticodon. You interacted with the ribosome that you put the triplet in. In that case, they form a complex together. Right? They duplex together, and the phenylalanine then, when you wash, all the cold amino acids come through. The one radioactive one that you have sticks to the filter, which says that it sticks to the ribosome, which says that phenylalanine, this tRNA with the AAA is the anticodon. So that UUU is the codon for phenylalanine. So it's sort of an interesting, it's a simple little experiment. You could do it in a lab now as a lab exercise. Wouldn't be any problem. If you did it, you wouldn't use radioactive phenylalanine amino acids. You use fluorescent amino acids because they're much safer to work with and easier to get rid of and dispose of. back then, just because we were able to radio label amino acids, we were able to do this experiment. So the genetic code was sort of defined because of that availability of those isotopes. If we look at the code, it looks like this. The biggest thing about the code is it's degenerate, and what that means is that there's more than one triplet that codes for each amino acid. So more than one triplet, which is a codon or an amino acid. Arginine has 6, serine has 6. Methionine is the only one with a single. Lysine, tyrosine, they all have others. Have doublets in there. Some of them have 4, threonine, proline, alanine, and so forth, have four codons, but all signify the same amino acid. There's a few other things you can play sort of games about these things. For instance, at the second position, at position 2 is a purine, there's a adenosine, right? There's a purine, adenosine, here's another purine, let's see, adenosine, where's the one that's a different one? Where's the guanine? And here's a guanine, adenosine, right? Guanine. Anyway, the third one is, if the second position is a purine, then the amino acid it codes for is charged. So adenosine, aspartic acid, adenosine, If position 2 is a pyrimidine, the amino acid is hydrophobic. Here, uridine, pyrimidine, valine is hydrophobic. Here's urine, pyrimidine, isoleucine is hydrophobic. So we can play games like that. We're not sure exactly if that's meaningful or not, but it seems to follow that. So evolutionarily, it could be important. We don't know. Remember, if you have triplet code, you have 64 you have a lot of possibilities there. All of the codes, all of these possible triplets essentially code or are codons for amino acids, except for 3, UGA, UAG, and UAA, which are stop codons. So they indicate termination of protein synthesis. And this is what we call the genetic code. You probably had in biology when you were in high school, and that's pretty much what happened. Now, the tRNA molecule